So I'm going to give this talk together with my colleague Josh from NVIDIA. And this topic I'm especially excited about because it combines three exciting things like big computers, so exascale, deep learning, and climate change. So this is the team behind the effort. I want to thank everybody on that slide for their contribution to make this a success. So thank you very much. I think even like some in the audience today, like math. Okay, so we are interested in extreme weather phenomena. So for example, if you think about Hurricane Katrina flooding New Orleans in 2005, or Hurricane Harvey flooding downtown Houston in 2017, you will see that these extreme weather phenomena, such as tropical cyclones or hurricanes, have a very important impact on economy and people living in these areas. So there are these black swan kind of events which cost about like $10 billion damage for like an estimate cost for each event. So for example, in 2017, there were like $200 billion worth of damage incurred by like the aggregate of all events over the whole US. So, but also like there are smaller scale events like atmospheric rivers, which are basically like atmospheric winds, currents, which can transport water over long distances. And they are responsible for 50% of all the rainfall in California. So what you want to do, you want to understand these events better because they can also cause like local flooding, but also can have an impact on the frequency of forest and the severity of forest fires. So when you think about the Santa Rosa campfire last year, I mean a lot of lives got lost, a lot of homes got lost, forests got burned, and we had a hard time breathing down here in the Bay Area for a couple of weeks. So we want to understand these events. And especially when you think about climate change, what you want to do is you want to understand, will there be more hurricanes or fewer? Will they be more intense, for example? Or will it stay the same? And also, will it make landfall more often, right? Because like insurance companies and like disaster mitigation strategies, they all need to like have an idea of what they need to gear up for and reserve funding and prepare. But also like for the atmospheric rivers, as I said, since they are responsible for a lot of rain in California, especially here, they can help mitigate droughts. If they become more frequent and carry more water, we might get fewer droughts. But if they, like, I don't know, if they change their directions and they get fewer of them, we might get more forest fires. So that is important. So when you think about how a typical climate data analytics you find in, let's say, in the public magazines and the IPCC climate channel, like the Climate Consortium report. So what they usually do, they have these high fidelity simulations. So this comes out from a climate simulation code. It's the CAMP5 data set. It's a 25 square kilometer resolution. So this comes out of your climate simulation. You ran on a big computer, like, for example, like the one we have at NERSC or like other computers in the DOE. And you have like tons of them. And you have basically, for 100 years, or like 100 years, you have like a 3-hour snapshot of like different realizations of the climate. So what people then do is they take this and compute mean and standard deviation, for example, for temperature, and then they make this plot. So that means you have a variable reduction from 40 million variables in a 3-hour interval to like order 1 variables, like maybe sea level rise, temperature rise per year. So that's quite steep, and I think you can do more with that data. So, and this is what we are aiming for. So what we want to do is we have this very high resolution data, and we want to detect hurricanes and atmospheric rivers to basically enable a geospatial analysis of these extreme weather events. So you want to answer like, is, for example, like the Gulf of Mexico more prone to hurricanes in the future, and there are a lot of oil rigs, for example, so that can impact the economy like heavily. And also, we want to develop a flexible and scalable detection algorithm, right? So what people do now, people who try this, they do basically what computer vision did 10, 15 years ago. They do manual feature engineering, run their algorithms, and then do these predictions. But when the underlying dynamic changes of the climate, then also these algorithms become invalid or inaccurate. And furthermore, when you think about exascale computing, so like the floating point 64, so double precision exascale computing, which is a big research topic in the DOE right now, at these machines, we might be able to get simulations with 1 square kilometer spatial resolution. And you don't want to trash this, right? You want to really make use of this. So your simulation is ahead of the data analytics, and that is what you want to fix. So what is the challenge here? So we interpret this whole thing as a climate segmentation problem, where we have 3 classes. So there's the background class, which is basically everything we're not interested in. So there's still a lot of stuff going on, but it's not of relevance to us. Then there are tropical cyclones or hurricanes, and then there are atmospheric rivers. So these are the 3 classes we're looking at. And we know that for these kind of like tasks, like image segmentation, deep learning has proven very successfully, for example, in autonomous driving. So what are the differences here? So first, the climate data is quite complex, so we have a very high class imbalance. And that is because in the future, these events are still rare, right? That is good, but on the other hand, it's a bit tricky because 95% of all the pixels are background. We also have like the shapes. When you think about a street scene segmentation, you see a car driving by. The angle at which you see the car changes, but the car is a car. It has like a defined shape. Whereas these things don't, right? So they can grow, they can shrink, they can dissolve, they can bend, whatever. And when you, for example, look even at a static image of a hurricane, so where actually are the boundaries of the thing, right? You can ask different people, and they might tell you different things. So that's a bit tricky. And you have different input channels from the simulations. So the simulations don't generate these nice RGB images. They actually generate like 16 physical observable channels, like wind speed, humidity, temperature, pressure. And you need to cope with this. And they're very vastly different in scale, so you need to do some normalization here. And also the background. The background is not static, right? Again, come back to the street scene. You have usually a very slowly moving background. You don't have a lot of stuff going on here. Whereas here, the background, there's a lot of stuff going on. It's like you have seen this on the video. It's like very rapidly changing. So that's also a bit tricky. So network needs to be able to distinguish between this and the actual events. OK, so let's talk about the challenges for deep learning in this case. So the best working approach is still supervised deep learning, and you need labels. So it's not like you cannot upload these things to Amazon Mechanical Turk and let people label it, because you need some expertise in finding these. So what we did instead, we used these old algorithms people designed for detecting these objects and used them as labels. So I will talk about this later. So basically using an old school heuristic-based method to feed this more modern deep neural network approach. So when you define a neural network architecture, you want to look at a balance between compute performance and model accuracy, right? You want to have a model which is good or big enough to get a good accuracy, but on the other hand, you want to be able to train it fast enough, right? Because you want to iterate over hyperparameters, for example, and for that you don't want to wait 2 weeks. And also for changing the network topology, you want to basically do this rapidly. You don't want to code it up in C++ or whatsoever. Instead, you want to use a high productivity framework. So that's, I think, important. And a lot of practitioners actually use this. And performance optimization, when you look at a lot of HPC codes, so let's put this multi-physics codes aside. When you look at a lot of HPC codes, they have 1, 2, 3, 4, 5 very compute-intensive kernels, which you can optimize the hell out of it, and then you have an efficient program mostly. Here, you cannot optimize every single kernel because these deep neural networks consist of different kernels with different input parameters and tons of them. And what you need to do is optimize the whole thing, the whole pipeline, right? From reading the data, feeding it to the GPU, processing it, and then in the backboard propagation step to reduce the gradients. I think we'll talk later about this. So this is a more complicated issue. And then you need to tweak the hyperparameters, like the learning rate and these kind of things, kernel sizes to get a good accuracy and converge in the first place. At large scale, what you have additionally is that you have tons of data, and you need to feed this to the GPU in a very efficient way. So, for example, even if you have an HPC file system, you have usually HPC system, you have a shared file system, and you don't want, for example, 20,000 GPUs hit the file system at the same time. That is usually not a good idea. So you need to make efficient use of this. And also, we do data parallel training, so you need do a lot of all-reduced kind of synchronous reductions. And if you do this across 27,000 GPUs, you need to do this very, very fast because these GPUs are very, very fast. And if you're imperformant, your GPU will stall waiting for that. And again, when you scale out, you cannot just use the same hyperparameters. You need to adjust them to maintain accuracy. So the issue is this is an unsolved problem, this hyperparameter tuning at scale, or how you bring how you basically develop a set of hyperparameters you found at small scale to like large batch. That is still an open problem, and I don't want to claim we have solved this. We employed some strategies to mitigate this issue, but this is still research. Okay, so label creation. I talked about these algorithms, so like how do they work? So this is an example for the atmospheric rivers. We start with this data here. So we have like water vapor, wind speeds, you see the vectors here, and humidity. And then what you do, you compute something which is called integrated water vapor transfer. It's like a feature, if you want, right? So you end up with this map, and then you think, oh, it's cool. So atmospheric rivers, like, there might be these objects here, so you apply some thresholding at the 95th percentile, and you end up with this like distribution. And then you apply some domain knowledge, and you know that atmospheric rivers never occur around the equator and never at the poles. So you basically mask out these regions, and you end up with some AR candidates. So these are the ones. So that's one thing. And the other thing for hurricanes, you do a similar thresholding approach, but here you need to find the hurricanes first, because so what you're basically looking for, you look for regions of high vorticity and like certain pressure gradients and I think like certain water vapor values. You basically find candidates, you draw a bounding box around them and apply your thresholding, like flood fill thresholding to that. So here you can already see that this label is pretty, not ad hoc, but it's not like a canonical choice, right? It can be bigger, it can be smaller, whatever whomever you ask might give you different answers. Okay. So here I hand over to my colleague Josh. He will talk more about the implementational details.
Thanks, Thorsten. So as Thorsten mentioned earlier, one of the, I guess, challenges for deep learning, or one of the things we wanted to use for deep learning is high-level frameworks in order to enable rapid prototyping and swapping out networks to really be able to tackle this problem of efficiency and compute and accuracy. So the framework we chose was TensorFlow. So TensorFlow is a high-productivity deep learning framework in Python with a C++ backend. What's nice about TensorFlow is even though you're writing in Python, it leverages very high-performance libraries in the background to do very efficient compute on GPUs, for instance, using cuDNN for convolutions. One other feature of TensorFlow is that it's a graph-based, it uses a graph-based execution pipeline. So, you basically form your neural network, your compute as a graph, and TensorFlow will actually operate this in sort of an asynchronous, thread-based manner, which actually introduces some challenges, which I'll point out later in the talk. Because TensorFlow is built on Python, it actually enables you to leverage some existing Python modules in a fairly straightforward way into your input pipeline or into your compute, if you so wish to do this. Kind of the next major library that we depended on top of TensorFlow was something called Horovod, which is a library developed by Uber. So what Horovod does is it basically can take an existing single worker TensorFlow program and in the background basically wrap it and allow it to run in a data parallel manner with fairly straightforward wrappers. This is in contrast to kind of more native distributed models in TensorFlow, which require a bit more code changes in your actual TensorFlow script. This is a little bit more transparent. One of the key features that we liked about Horovod and why we picked it was that it actually can leverage MPI for worker and coordination control. And I like to point this out because MPI is ubiquitous in HPC. I mean, it's been around for 20 years now, so you can expect MPI to be installed on any large cluster targeting HPC applications. So like the government supercomputers we've worked on or similar computers of that nature. Additionally, Horovod, like TensorFlow, can leverage optimized libraries to do the real bulk of work. So in this case, Horovod for the collective operations themselves, the all reduces, et cetera, it's able to use either MPI or Nickel, which is the NVIDIA Collective Communications Library, which is very fast on GPUs. So for this study, we actually had the opportunity to test on two different systems, PISDaint and Summit. And what I find very interesting about this is that PISDaint can be kind of considered the previous generation king. It was the #1 GPU supercomputer prior to Summit being installed. So it actually gives us a really interesting contrast between where we were and where we are now. I don't want to go too much into the details with PISDaint, but I do want to at least go through some of the specs of Summit because they are relevant. So Summit's installed at Oak Ridge National Labs. It has 4,609 nodes. Each node is equipped with 6 Tesla V100s and 2 Power 9 CPUs. There's very fast NVLink peer-to-peer connections available on the nodes, and also a kind of power-specific feature is that there's NVLink connections between the CPUs and the GPUs as well. So on x86-based systems, you actually are limited to PCI Express for that channel. Each node has 800 gigabytes of really fast NVMe SSD storage, which is something that we end up utilizing. And I guess the big number there is that it has 3.45 exaflop FP16, half precision peak performance. So before we delve too much into the actual details of what we did and what we changed to make this work, I kind of wanted to break down the scaling problem and talk about the different considerations that you encounter at each level, from a single GPU all the way up to your multi-node problem. So this is actually a fun clip art diagram that Thorsten made of a Summit node. The 6 green rectangles are V100 GPUs, and the burgundy squares are your P9s, but it's kind of unimportant. So first we'll consider the single GPU problem. So on each GPU, we're running TensorFlow. TensorFlow is using cuDNN. It might be using HDF5 and some other libraries for your data management. So these are kind of the considerations that you would make at this level. So first of all, is my TensorFlow model efficiently using GPU resources at this scale? So here, we basically have our single worker. We want to make sure that we're achieving high peak memory bandwidth usage, high peak flop usage of our TensorFlow model. If we're not, this is the place that we should be focusing on fixing that. Okay? The second thing we want to look at is our data input pipeline keeping up? So as our training speeds up, are we actually feeding these guys rapidly enough? Or are we introducing stalls? If we're introducing stalls at a single GPU, you have no chance at scale, right? So you want to fix that here. And then also, this is when you can start to say, is my TensorFlow model providing reasonable results? You might not run the training on your full data set, but you can at least see if your model is doing something sane. So once we have this all figured out, we can expand our scope to a single node. So here's a single node problem. Basically, we replicate the single GPU work on each of the GPUs on this node, and then we tie them all together with Horovod, which uses nickel and MPI to coordinate and communicate between all the GPUs and perform collective operations. So at the single node problem, we're assuming here that we've solved, we understand the single GPU problem pretty well. So here we're actually mostly concerned about issues with scaling out. So first we want to consider, is my data input pipeline still keeping up with my TensorFlow model? So just because your data input pipeline kept up with 1 GPU doesn't mean it'll keep up with all 6, because now we've split the on-node resources across, by 6 GPUs. So we want to make sure that that's all sorted out. Here we also want to start talking about whether or not our data parallel TensorFlow model is still providing reasonable results. So we've now increased our batch size, we've done different things, and we now need to look at and see, do we need to tune hyperparameters, do we need to do things of that nature in order to maintain convergence and accuracy? And this is where we actually start to talk about communication. So we look at, how is my performance scaling over PCI Express or NVLink, which are kind of the on-node peer-to-peer connections available to us here. Look at that and start to understand, how is the communication interacting with my TensorFlow model? So once we understand the single node problem, we can move on to the multi-node problem. And what we actually find is that the multi-node problem is quite similar to the single node problem. Once you have, don't know why I did that. The multi-node problem is very similar to the single node problem, except the nature changes just slightly. So first we consider, is my data parallel TensorFlow model still providing reasonable results? Basically, to the TensorFlow model, it doesn't matter if I'm on a single node or multi-node. At this point, it's just, I'm increasing the number of workers. Am I making reasonable changes to deal with that for convergence and accuracy? For scaling, we also still ask the question, how is my performance scaling over NVLink, but in this case, plus InfiniBand? So now, instead of being in kind of this nice encapsulated node where everything is fast and all of our communication is fast, we're introducing relatively slower cross-node network connections. Is our communication strategy being able to withstand that? And then now we also ask, how do I distribute my data across so many nodes? As Thorsten pointed out, when you're dealing with remote file systems, this becomes a real challenge. So this slide actually shows the 2 models that we looked at in the study. Tiramisu on the left, DeepLab V3 on the right. So Tiramisu is actually the network that we started out with. DeepLab V3 is what we ended with. So these networks are both UNet-based encoder-decoder segmentation networks. Basically, the idea is that the encoder pass on the left of each of these extract features from your full resolution input. It goes down, and the decoder basically reconstructs a full-size segmentation mask from these features. These networks also have these so-called skip connections, which feed features at various levels of the encoder phase back into the decoder to improve segmentation results. So what we found is that Tiramisu, our first network, didn't actually perform that well. And the reason was that the segmentation masks that it produced were way too low resolution. They weren't able to capture some of these really fine-grained features in these atmospheric phenomena, these tropical cyclones, like with all these little tail-offs and all that stuff. So we decided to take advantage of the fact that we had a lot more compute on Summit available to beef up the network. So we switched to DeepLab V3, which actually has 43 million parameters versus 7.8 million, so a lot more parameters. Requires 14.4 teraflops per sample versus 4.2 teraflops per sample. Another way we actually increase the compute of the DeepLab V3 network is in the original model, the reconstruction actually used a bilinear interpolation to save on compute because it was too expensive to form a full resolution segmentation mask in the original network. But because we had an excess of compute available for us on Summit, we did a full resolution deconvolution in our version of the network, which improved segmentation results substantially. Okay, so now we'll talk about data staging. So again, we were talking about this multi-node problem. We need to figure out where we want to put our data, how we're going to split our data up, and how we're going to do this efficiently so we're not just waiting forever for our jobs to start. So we realized early on that at the speed that our network was churning through data, that we would actually require, at scale, an aggregate read bandwidth of 3.8 terabytes per second, right? So if you do the math and we look and we actually experimented with some of these systems, we found that this would not in any way be able to be serviced by the GPFS remote file system, which can only obtain about 400 gigabytes per second. So from that point on, we looked and we saw, hey, the NVMe is able to provide in excess of what we need, so obviously we need to get our data onto this on-load local storage. So that was what we targeted. So for our study, we basically took our full-size data set, we chunked it up, and we put 1,500 samples per node. But instead of having every single node read 1,500 samples from data, which is quite a lot of data per node, we established a strategy where each file was read once on certain workers and basically able to be transferred across nodes using MPI instead of the remote file system. The idea here is that we basically wanted to reduce any sort of redundant reads from global file system because that was very slow, whereas MPI is able to take advantage of really fast communication to transfer this data. So this actually enabled us to start up on Summit with data staging in like 3 minutes, around that sort, if I remember correctly. To do the MPI stuff, we use MPI for Pi, which is a nice Python wrapper for MPI calls. So then now that we have our data on the node, we need to talk about efficiently using that data in our TensorFlow pipeline. So again, like you can have all the read bandwidth in the world, but if you're not effectively hiding your data input behind your compute, you're still going to introduce bubbles, right? So we actually use the TF data API to handle some prefetching and shuffling and all this stuff, which basically TF data provides a really nice API for you to actually put some of this data input reading in the background. One issue we ran into is that HDF5 has this really fun serialization bottleneck. So if you actually try reading HDF5 files with multiple threads, those threads cannot actually read the HDF5 files concurrently from the same process. It serializes the reads. So in order to get around this, we actually wrote this Python function that would use multiprocessing to actually have multiple HDF5 reader processes essentially be able to read all these files concurrently, which ended up speeding up our data pipeline and gave us really good results. So this table here is actually a table of single node performance metrics that was obtained sort of midway through the project towards the end. I don't want to get too much in the details, but basically the idea is that we have the kernels grouped by all the various kernel types. There's forward, backward, pass, convolutions, and pointwise kernels. There's some nickel all reduce and some copies and transposes. The key points we want to bring up in the slide are as follows. So in the magenta section, we see that there's a wide array of different kinds of kernels that are being called in our network. So this kind of backs up Thorsten's claim that for these deep learning problems, there's not just 1, 2, 5 massive kernels that make up most of your compute time. There's actually quite a lot of different kernels of more or less equal importance that need to be considered. So you need to look at this problem holistically. In the green, we point out that about 50%, a little over 50% of our compute time is actually spent in compute-intensive kernels, which is good. This is something that we want. But in red, this is one of these interesting trade-offs. So like we said, in order to do rapid prototyping, in order to have this flexibility, we wanted to use a framework like TensorFlow. Now, this is where maybe one of the limitations comes up. So when you're coding in TensorFlow, you're coding at this very high level in Python. And TensorFlow, the backend, is allowed to make decisions in terms of where to place data, when to transpose data. It might have a data layout it wants to use that you don't want to use. And so sometimes you can find that your TensorFlow network will introduce a lot of extraneous data movement, data copies, and data transposes. So early on, we actually found that about 26% of our time was spent in some of, basically just data movement on the GPU or moving data to other buffers, which is not so great. But it turns out that if you have a little bit of insight into how the backend works, you can sort of game your network and your data layout in various spaces to sort of optimize these away, or at least try to reduce them. And then the last point here is this small orange section 1.7 of GPU idle time. This just shows that even with all this optimization of the data pipeline, we actually still do see a little bit of a performance penalty for having the input, having the GPU wait on input. Okay, so that was some profiling data, and we're talking about the input pipeline. But now we need to talk about how do we actually do the communication. So like we said, we were using Horovod, this library for communication, to actually distribute our training. So Horovod consists of two sort of major pieces. There's a coordination phase, and there's actual collective operation phase. So as I mentioned earlier about TensorFlow, TensorFlow is uses a graph-based execution pipeline. And so this means basically one big thing is that you're not guaranteed that your order of operations will be the same either across batches or across workers, right? But in order to do synchronous all reduces, you need to ensure that all workers are submitting all reduce operations in a consistent order, or else you have deadlock. So in order to address this challenge, Horovod had an original strategy that looked like this. So basically at a given, Horovod runs at this fixed tick rate, and at every tick, it checks every worker. And so in this case, we have an example with 4 workers here, worker 1 through worker 4, and they each have a list of tensors. They say, hey, I'm ready to all reduce these. So you can see that the lists contain different tensors. They can come in different orders. So what needs to happen is, or I guess in the original strategy, what happens is worker 1, or rank 0, for those familiar with MPI speak, gathers all the lists from all the workers. Rank 0 does a local intersection. It basically just figures out, okay, what are the common tensors across all these workers, figures out that list, broadcasts it out to everybody else, then everybody does their all reduce. Now, a strategy like this might be fine at small scale, but basically for those familiar in HPC, this many-to-one, one-to-many type communication pattern can suffer quite substantially once you increase the number of nodes, right? This is a linear communication strategy. We found that once we started scaling out, we were spending more time thinking about how to all reduce than actually all reducing, right? Or even computing. So one of the optimizations we made at Horovod for our project was to change this control plane to a tree-based control plane. So take this linear control strategy and turn it into a logarithmic one. And we found that this substantially increased the responsiveness of Horovod and allowed the coordination part of the communication to get out of the way. And we were spending more time doing all reduces instead of thinking about doing all reduces. So in this strategy, basically all the workers, rather than submitting to rank 0, they all submit to nearest neighbors and do a very nice tree-based pattern. Okay, so now that we have the coordination out of the way, we need to talk about the communication, or the collective operation speed. So now we can do all reduces fairly rapidly, but how are those all reduces actually performing? So it turns out that originally Horovod was able to do one or the other, MPI or nickel. And it turns out that there are strengths and weaknesses in both MPI and nickel that we wanted to exploit for this project. One of the strengths of nickel is that nickel is a library that's developed to operate very rapidly on GPUs. It can take advantage of really fast interconnects. NVLink, it uses GPU kernels to do the actual all reduce operation. But original nickel had used a ring-based all reduce strategy. And this strategy does not scale either. So a ring-based all reduce strategy at small scale is fine. When you go to large scale, you end up just suffering from massive latency. So that's the strengths and weaknesses of nickel. MPI has strengths and weaknesses too. So the strengths of MPI are that MPI implementations are often optimized for the system they're on, the topology. They have a lot of topology-aware algorithms can make very optimal choices in terms of how to do communication. But MPI is not necessarily capable of taking advantage of GPU resources, fast interconnect, things of that sort. So what we decided to do was try and combine the strengths of both of these things. We decided to say, okay, let's take nickel, we'll let nickel do all reduces on the node, and we'll let MPI do all the communication cross nodes. So what we do is we use the fast ring-based all reduce and other collective operations on the node, and we use MPI cross node for, okay, weird. We use MPI cross node in order to take advantage of faster communication algorithms across the cluster, so maybe tree-based, things of that sort. This algorithm here that I'm pointing out is a little bit weird and Summit specific. Basically, we found that we wanted to create a strategy that would only result in one cross-node all-reduce per virtual NIC. So that's why we have this kind of all-reduced for broadcast type strategy. But we turned out that this strategy worked very well and improved our performance substantially. And probably one of the last features we developed regarding communication was this gradient lag, or at least we implemented this in our code. Basically, with lag 0, this is the conventional case, fully synchronous. So for each step, you do forward pass, backward pass, you get gradients. You need to all reduce them and wait. Then you update your weights. So what lag 1 enabled us to do was basically update with previous steps gradients to give us a little bit more time to complete the all reduce. Basically, this just enables us to have more all-reduce computation, or more time to complete the all-reduce computation without hindering our compute speed. We'll show some results, but this is actually a very substantial improvement. Okay, so now we'll actually go on to some data. So this plot here is a plot generated from PISDate. So this is some early exploratory data that we were looking at, trying to assess the importance of using node local memory. So here in red, we have FP32 local storage results. In blue, we have FP32 global storage results. The x-axis is number of GPUs on PISDate, and the left is throughput in images per second. So what we see is that on PISDate, running on old GPUs, so P100s, FP32, which is the slower network, still, even at a fairly modest scale, has a 10% performance penalty for using global file system. So this result here showed us immediately, using the global file system at the scale of Summit with an FP16 network with V100 GPUs using Tensor Core, we just had no chance. So that's what this slide's supposed to show. Now we'll move on to the exciting stuff, which is the scaling results. So as I said, we actually looked at two different networks, Tiramisu and DeepLab V3. So Tiramisu, but in order to make to kind of finish the job, we decided to scale out both Tiramisu and DeepLab to almost the whole of Summit. So these are the results for Tiramisu. And here, color scheme's changed a bit. So red is FP16 Tiramisu results on V100 on Summit. Blue is FP32, also on Summit. And the purple, if you can see way down here, is the results on PISDate, FP32. So we can see that, quite a substantial performance improvement between Summit and PISDate, just due to the hardware improvements available, the better FP16 performance. What we want to point out here is that, I should point out, the lighter colored red and the lighter colored blue represent the lag 0 or fully synchronous case, and the dark color represents the lag 1 case. So what we find is that with lag 0, the normal fully synchronous all reduce, we get pretty decent scaling. But we see that FP16 does suffer from some communication bottlenecking. But it turns out by turning on this single step gradient lag, tightens it right back up. And so for this network, we're able to achieve around 500 petaflops for FP16 and around like 180 petaflops FP32 on nearly the whole of Summit. And then these are kind of the interesting results here. So this is the scaling for DeepLab V3+. So again, story is very similar, but we can see that DeepLab V3+ is a larger network, has more communication volume. So we actually see that FP32 and FP16 both suffer from communication bottlenecking a bit. But again, like with Tiramisu, introducing the single step lag tightens that up, the curve up quite substantially. And we see that on these plots, we're just shy of that 1 exaflop mark that we're aiming for. But wait, there's more. So basically, this plot actually ends slightly before the full summit size. I think it's around 4,500 nodes. After we generated this plot, we realized that there was a few small performance optimizations we could make, namely modifying our data layout to remove extraneous copies and transposes that actually gave us, I think, around a 10% performance boost, if I remember, something around that, just by changing the data layout in Python, so a couple code line changes. And we also added 60 more nodes. So our final result was actually at 4,560 summit nodes, and what we achieved was this. 999 sustained petaflops per second. I think Sean and the Gordon Bell talk like to joke that, if we were in marketing, we would have just rounded it up to 1, but we're scientists, so we had to keep it at 999. But if we consider the peak that we actually achieved, we hit 1.13 exaflops per second with this network on Summit. So again, at 4,560 nodes, which equates to 27,360 GPUs. So quite a big job. And so for that, as our introduction said, we won the Gordon Bell Prize along with another team from Oak Ridge this year. This is the picture of all the smiling people on the stage accepting the award. So I'm actually going to turn it back to Thorsten to kind of finish out the talk on convergence and conclusions.
Yeah. Thank you. So, by the way, I'm not smiling on this slide. So let's talk about convergence a little bit. So this is a plot from the earlier Tiramisu network. We did some more extensive convergence studies than with the deep lab network. So what you can see here is when you go from, so just look at the FP16 for the moment. When you go from 380 GPUs to a 4 times bigger scale, 1,500 GPUs, we'll get about a 2.1x improvement in solution. So I want to say that even if we do this batch parallel training, which in the conventional HPC sense would look like weak scaling, so this is actually a strong scaling, right? We want to try to improve the time to solution by scaling out. So I have to say that you might say, okay, 4 times more GPUs, 2.x improvement doesn't sound very great. But the thing is also that you, with more aggressive hyperparameter optimization, you can get a better result here. But it's also availability of the machine. So Summit was highly contested among other Gordon Bell teams, and also a moving target, I would say. So this is why we will time limited to optimize this fully. But nevertheless, even with the set we came up with, we do a decent job. So Josh talked about this importance of this lag to get a better scaling efficiency. The question is, does your network still converge, right? You might think, okay, if I have outdated gradients, when you think of this as an optimization problem, you're on your manifold, and when you compute you usually compute the gradients and go into along the gradient for certain step size given by the learning rate. What you actually do with the lagged approach, you basically update with gradients which are outdated. So technically, they do not point into the right direction from where you are currently on that manifold, right? So, and what you basically get, since we also use some gradient boosting technique called LARC, is some kind of a Brownian motion behavior. So at the beginning, you basically have no clue of where you're walking, but the network catches itself and then outperforms in time actually the no-lag version, and that's what you want to see. So of course, looking at this, you might want to think, okay, maybe combine these two techniques, so do basically warm up using a fully synchronous approach, paying the performance penalty, but then maybe after 2,000 seconds, you just switch to to the lagged version, and then you converge much better. So this is what I would do now after seeing this plot and after the Gordon Bell, but so we stick with this version here. Okay, so these are the segmentation results. So on the left-hand side, you see the predictions from the network. So blue contours are atmospheric rivers, red contours are hurricanes or tropical cyclones, and on the right-hand side, you see the same for the labels. So I want to point out 3 things. So number 1, the IOUs, which is basically tells you how well the labels and predictions overlap, is acceptable. One thing, though, you can tweak technically the network parameters to reproduce the labels quite nicely, but on the other hand, we don't want to necessarily do this because the labels we started with were not very optimal. The problem is that, as I said, these algorithms are pretty aggressive. So when you, for example, look on the right-hand side, what you see is that the labels are very sharp. They have very sharp edges, whereas these labels look a bit more wobbly, a bit more smooth. And that is totally fine because, as you've seen from the introductory slide, they're where these hurricanes start and end, or the atmospheric rivers, it's really hard to define, right? So this is a totally acceptable result. The other thing is what you see is continuity in time. So here you see a lot of flickering, right? Atmospheric rivers vanish and come back. And that usually means that, for example, in 3-hour time interval, the old algorithm finds a hurricane or atmospheric river. In the next 3 hours, it doesn't find it, it's gone, and then it comes back. Of course, it's not going back and going away and coming back. That's not true. It's actually there. It's just that the algorithm is too aggressive. The network, however, so even if we did not implement time dependence into our network, we do a by image segmentation, and we also shuffled images. There's no temporal correlation whatsoever. It somehow learns features which are more continuous in time, right? So that is quite interesting, and we might want to improve on these results even by taking time dependence into account, but that would be a further development. Okay, so we talked about what we did in Gordon Bell, so what happened since then? So first thing, I think Sean can talk more about this, is that this hybrid OReduce Sean talked about is actually now available in the upstream Horovod branch, right? I think, so NVIDIA did basically the groundwork, and then there was a guy from Amazon cleaning it up a bit, and now it's available. The control plane algorithm, so I think this tree-based method was a bit too complicated for Uber. So, and they have now a slightly modified version, which is expected to give similar performance, so also reducing this crazy one-to-many-to-one communication pattern, basically by using OReduce on bit vectors to figure out which tensors are ready. So that will be available soon. I think there's an open pull request dangling somewhere, and it will be incorporated at some point, and then you can benefit from that as well. So nickel, as Sean mentioned, that when we used it, I think it was 2.1 or whatever, it just had a ring-based OReduce, which is not very scalable. So the new nickel also implements on top of that a tree-based OReduce for better scalability. So you might even try to compile Horovod solely against nickel and try to use purely that and see maybe it just works. And if you are at moderate scales, it might just work out of the box, which is great. So we at NERSC, some more from the science side now, what we want to do. So we started an effort called ClimateNet, which is a guy, Karthik, at NERSC is leading. Because our labels were not super great, we want to basically do some labeling, and we basically started some kind of Amazon Mechanical Turk for domain experts. So we have a web portal where you can, as a climate scientist, you can go and label these hurricanes. Also, this project serves as a science problem for the ISC HPC 19 Student Cluster AI Challenge on a cook down. So we can't expect students to bring Summit in, or a Summit scale system. So what we did, we basically boiled it down a bit, made the network a bit cheaper, and also the images, we cropped the images that they are smaller size so that you can do this nicely on a smaller system. And also, what we learned about file systems and scalability of deep learning approaches, especially what requirements you have if you have super fast GPUs. That basically also went partially into our new procurement, the NERSC parameter system. And there is a talk about this, I think, on Thursday, where we present this system at NERSC. So it's basically a GPU-based system at NERSC. Okay, so the conclusions. So deep learning and HPC come together. I think you'll see that everywhere. So, and you can achieve exascale performance. Exascale is in italics here because it's not what HPC people call exascale, right? It's it's the FP16. But the main point here is if you can get along with mixed precision or FP16 reduced precision arithmetic, you are actually having exascale capabilities there. They're right there right now. And so contemporary HPC systems can tackle deep learning problems very well because they have very high-speed interconnect, usually a lot of memory, and it can hold a lot of data. And so HBO, especially for convergence at scale, is still an open problem. We would like to see that solved at some point, but this is really hard. A lot of people are working on that. On the other hand, the software enhancements with that will benefit the deep learning community at large. right? So, and now actually if you want to tackle, if you have a cool strategy for doing hyperparameter optimization at scale, you can now take this stuff we did and employ it and test it out, right? Before that, it was not easily possible. And we think that deep learning is opens, like, there's a lot of applications and low-hanging fruits in the science space where you can deep learning to do interesting things. Thank you very much.